Okay. Hello. Yeah. So this is gonna be the workshop going on shaders, and the specific shader that I'm gonna be like breaking down during the workshop is going to be the Kuwahara filter that I've made. And first, just like give you an idea of what the filter actually does. So then, this is just a random environment that I got for free from Epic's like new Fab store. They give out a bunch of free assets. When you're testing out shaders like this, unless you actually want to go and build the entire environment yourself, I would always recommend just getting assets from online, just so it makes it easier to test out. But yeah, so this is what the scene looks like by normal, and then when we apply the blur filter to it, you can see everything kind of gets blurred together, which is the effect that we want. And then it kind of gives off like the feeling that the scene's been painted as opposed to like hard edges, which is kind of what the whole point of the filter is. It basically just smooths out a lot of the edges and color values as well. So it gives it a very stylized look, which is the main reason why you would actually want to use a filter, right? But yeah, you can make the effect a lot stronger if you wanted to. So like, if I wanted to do like 8, for example, right? I could do 8. This is basic. Kind of think of these as like the intensity parameters. The problem with doing it at 8, it does give you like a much stronger filter. Then because like it is still a game, you still want to be valuable for gameplay. This might be too strong of an effect for like an actual game, which is why normally I stick to somewhere around like the 4 to 3 range, which is what I found works so well. Which is like this. Alright, for the 3, it's more so like this. So yeah, 4 to 3 is what I would recommend for actual gameplay purposes, but if it's just like a demo or you just want to see like how strong you can make it, then feel free to go higher than 3 or 4. But getting into the actual filter itself, it looks very simple, but that's just because most of everything that's happening is happening in this Kuwahara node, which is a custom node, so you can make a custom node. Custom node basically just lets you write HLSL code inside of here, which is where most of the actual filter happens. So you can come down here and here's all the code. I don't actually recommend writing your code directly inside of here because, I don't know, it just feels not that great to me. Instead, I just write all my code inside of Visual Studio. But that's up to you. I'll be doing a more in-depth breakdown of all of this in a bit, but for the actual setup, when you get the custom node, it comes with 1 input. For the color filter, you're going to need 4 inputs, which is the scene texture, the UV, the radius, and the view size. The naming matters, so name them exactly like this, or if you don't want to, if you want to name them something else, just keep in mind what you actually do end up naming them, right? But you want to add 4 inputs. Also make sure that your output type is custom float 3, and then I should also mention for the actual shader itself, you want to come into here and then put them into your domain of post process, because that's actually what it is, right? So after you have the custom node set up, you want to have all this code obviously, but after you have all your inputs set up, for the scene texture, you're going to want to take a scene texture post process input 0, which is basically you type in scene texture. The default node will give you scene color, but you want to come to the ID and you want to get the post process input 0. Getting the input 0 is important. Don't get one of these. The reason why is because you use channel 14 in the code, and then channel 14 correlates to this input process right here. So that's that. And then you just want to plug in the color to the scene texture. The radius, these are scale parameters, so scale parameter, and then you spell the name out and then you set the value. The default value is 5, but then you can change that in the instance. So like, I have it set to 4 in the actual instance. But then you get both of these, then you want to append a vector to basically combine them, and then get around, turn it around, and then plug it into view radius. View size is just view size. The UV is actually also a custom node. It's a very simple one. You just get the custom node. You don't have to add any inputs to it or anything. You actually want to delete the inputs because this should have no inputs. The actual code itself is very simple. It's just return get default scene texture UV, parentheses, parameter, comma, 14, parentheses, and then semicolon. So now you have everything inside the actual material set up. Now we have to talk about the actual code of it. So the code, let me open up Visual Studio. All of this part right here is just some like setup part. Is basically just saying that these three values are what we're going to be looking at when it comes to actually, like, these three values is what we're going to be storing for each of the pixels. The mean is just going to be the color, the sigma is going to be the variance, and the weight is how important that pixel is in correlation to the sample pixel. So this is all just a bunch of setup thing. So the first thing we're doing is defining a sample area, right? So a sample of a circle of pixels. We start by calculating the size of one pixel in UV space by dividing 1 by the screen resolution, which is view size right here. Dividing that by 1 gives us pixel size, which just lets us step exactly 1 pixel at a time, regardless of screen size. Because this whole the whole filter, it might seem like a lot when I say this, but it runs this entire code, like everything I've written here, for every single pixel on the screen, right? And so setting it to be pixel size based instead of view size based just lets it do that properly. And then for the init radius, it's just the value right here. Basically, it's just defining how big of an area we want to sample for every single pixel on the screen. The more you sample, the stronger the effect gets. The less you sample, the weaker the effect gets. One thing to note is with performance, the more that you sample, the bigger area that you sample, the more it will affect performance, because you have to calculate more stuff for more pixels. It's also why I don't recommend going up to those higher values, especially for gameplay purposes, because you want to keep performance in mind, right? So that's how this works. And then the next thing we do is, so now we have our like a sample size for the pixel, right? We want to divide that circle into 8 different regions, which is what happens here. But before we can like divide the circle into 8 different regions, we're actually getting a square sample, right? Because that's just how HLSL and Unreal works, where we're getting the center of the pixel and we're sampling a square around it, right? But we don't actually want all the pixels in the square, we only want the pixels within that circle, which is what this part of the code right here does. It basically just draws out like a line from the center to represent the radius of the circle, and then cuts a square, or cuts a circle into the square. So like it trims down some of the pixels that we don't actually want to calculate. So it just saves on performance a little bit. This is what this does, right? And then as for actually dividing the samples, get the proper code, it's just we use A10 offset. This basically just tells us like the direction. So like it takes, so from the center, like your pixel that you're calculating, right? From the center of that, it draws a line to the actual pixel, then tells us the angle of that line. And then we can use the angle of the line to determine which of the 8 regions we make that pixel falls into, right? Because each region will have its own set angles. So yeah, this is the code that actually divides or I guess like more technically, the float angle A10 it gives us a direction from the center of that pixel in radians, and that angle is converted into a value from 0 to 2 pi. And after we get that value, we split the circle into 8 equal slices of 45 degrees each, and then which is what happens here, the region part. And then based on the degree of the line to that pixel, that's calculated by A10 then that pixel will get assigned to one of the 8 regions depending on which direction it falls in relative to the center. So this entire chunk of code right here, all it's doing is basically just trimming down the sampling area, which is a square, into a circle, then categorizing all the sample pixels that are valid into one of the 8 angular like buckets, I guess we have to then be later so that we can later look at like its color values, variance, and all the other kinds of stuff, right? Which, speaking of, is exactly what the rest of the code in this for loop does. where you have the compute average color. Yeah, so right here we're just computing the average color and then the variance for each of the regions. So yeah, once each pixel gets sorted into a screen, then we start collecting statistics basically for all of the regions, right? There's three things that we're going to track for in each region. The first is the mean, which is the total weighted color. This basically stores the sum of all the pixel colors, and each of those colors gets multiplied by a Gaussian weight, which basically just means that if a pixel is, it's like we have our center pixel right here, right? And then we have a pixel that's right here, and then all the way out here, like near the end of the sampling area. The pixel that's closer to the center pixel that we're actually calculating the color for, that will get much more importance than the pixel all the way out here, right? And the reason for this is because these like sampling areas aren't always, they're based on the screen itself as opposed to like per object, right? So like let's say you have, I don't know, like a tree right here, but then behind the tree you have like concrete for some reason. Just go over there, right? The color values for the tree obviously are like a brown color, and then the color values for the concrete are gray color. For your sampling area, you might get, part of your sampling area might fall in the concrete, so you'll get a lot of gray values. We want those gray values to have a lot less importance in the color of the final thing, or of the final pixel, right? Which is why we have to use a weighted Gaussian. It also helps keep edges a lot better, which is another key reason why we're using weights, because most Kuwahara filters, like the basic version of it, doesn't actually use weights. But if you don't use weights, then your edges get a lot more distorted. So by using weights, you can preserve edges a lot more. Also, we haven't actually calculated the actual average yet. We're just collecting the total color so that we can average it later. And then the next component, or the next piece of data that we're also collecting, is the sigma, which is the total weighted squared color, which might sound a little strange, but it's exactly what it sounds like. Like squared color is just color squared, it's color multiplied by color. And then we need this to calculate variance later. Variance, we need to do this because like variance is based on the difference between the average of the squares and then the square of the average. So like variance equals average of squares minus square of variance, or squares of the average. So we need to track these squared values for each of the regions. And then lastly, it's weights, which is just the sum of all the weight, like the Gaussian weights in the area. This just keeps track of how much influence you've added to each region. Like close pixels get higher influence than distant pixels less influence. Later, we'll divide the total color and sigma values by this weight to compute the actual average and variance for each of the regions. Also, this whole thing runs for every single pixel on the screen. Each pixel will have this whole process applied to it as the game runs. So the next thing that we're going to do is choose and blend between the most stable regions. So now that we've actually gathered all of the different data, it's time to process it. So the first thing we do is compute the average color for each region, which is basically we take the total weighted color and divide it by the total weight, which is what's happening right here. And then that gives us a true average for that region, because again, weights are important, which is why we can't just take the mean by itself. You have to divide it by the weights to actually get the proper average. Next thing we do is calculate the weight, or the weighted average of squared color, and then subtract it from the square of the average color, which is what's happening right here. This gives us a float 3 variance value, one for each of the different RGB channels, but we don't want a float 3 variable. We just want a single variable, like a single scalar variable that tells us that basically represents the entire region as like one brightness value, right, as opposed to all three. And the way we do this is by applying perpetual luminance weighting, which is what we're doing right here. This basically says that the green channel matters the most, about 71%, the red channel matters the second most, about 21%, and the blue channel matters the least, about 7%. The actual numbers for this, I don't know why those are the numbers, but it's something called luminance relative factors, I think. It's like a scientific term. It basically just is like, to the human eye, this is the amount that colors matter, right? So when we're taking these So when you're taking the float 3, which has all the different RGB channels that you want to convert into one single channel, it's important to weigh them properly, which is what this happens right here. And so then this gives us a brightness based measure of how like noisy or unstable a region is. And then the last thing we want to do is basically find the two most stable regions. So then we loop through our 8 variance values, keeping track of the smallest and the second smallest. The lowest variance is the region that we trust the most because it's the most uniform, has the least noise, it has the most similar color values to it, right? And the second lowest gives us kind of like a backup to smoothly blend between, because if you only take the lowest variance, then we might get a lot of like blocky textures or very hard cutoffs. But by using two of them, we can blend well between those two. This basically just ensures that we have like smooth transitions and avoid harsh boundaries. That's this code right here. And then finally, the last thing we have to do is choose and blend, or not choose, sorry, is blend the two best regions and then output the final color. This is really simple. We're basically, because now that we have our two regions that are the most stable, we want to blend their average colors together. We don't want this blend to be like a 50-50 because we do have one region that is less, that has less variance than the other one, right? So we want to give that region a bit more weight in the actual blend, because the second least variance region is meant to be more like a backup smoothing thing as opposed to like the main thing, right? So the more stable region gets the higher weight in the blend, and the second best region basically just helps to smooth things out to avoid harsh edges or blocky transitions. And this is the final color. So the final color is right here. But the last thing you want to do is return min final color flow 3111. This isn't absolutely necessary, but it's like a very good safety check. All this is doing is making sure that the final color that you actually output has a is like within the valid 0 to 1 range for brightness, especially when you have like HDR lighting conditions that Unreal does, because the brightness value can become more than 1 for any number of different reasons, and if it does become more than 1, then it will get heavily overblown. So we want to avoid that as much as we can. So this is like the final little check to make sure that all of the different brightness values stay between 0 and 1, so that we don't have any scene in our, so that we don't have anything that's overblown in our scene. But yeah, that's how the actual Kuwahara filter itself works. Most of it is in HLSL, but you do have to like set up some of it outside of the HLSL code itself, inside of the shader material. Okay, real quick, here's all the code. This is this initialization. This is where we sample a circle of like the pixels. And this is where we divide the circle into 8 angular regions, or this right here. And then this is where we're computing the average color and variance for each of the different regions. Then we're just choosing which, we're basically like calculating the actual averages based on all the weights, and then based off that we choose our two regions for blending later down the line. And then to choose them, then most of the regions is just where we do the actual blending portion of it. That's how that all works. And then you basically just want to write everything in Visual Studio and then copy it into your custom node into right here is what I've done. But after that, if you've done everything correctly, it should work. So then you have a fully functional Kuwahara filter. And then to actually make it an instance, your actual material, I guess I should also talk about like how to make a material. So just right click, material. Probably should have done that sooner. But to make the instance, you just right click the material and then create material instance, then you get material instance. The reason why you want to use the material instance as opposed to the actual thing itself is because the material instance, you can just come in and change the values as opposed to having to go in here and then change the values inside of here. But yeah. I guess the last thing you can do is show off the filter in like different environments. because this is kind of the environment that it's meant to work in. Like if you already have an art style that's leaning more towards stylized, and then your models kind of reflect that, adding this on top can give you an even more stylized look, but it can work in like more realistic environments as well. So like this is another free thing that I got from Fab. It's a brutalist office texture. I think this is the level. Let's hope my Unreal doesn't crash. But this scene specifically takes a while to load because it has a lot of objects in it. That is wrong now. Okay. Where's this map then? Yep. One thing that's I find a bit interesting is the FPS and what the filter does to it. Because normally the filter will lower your FPS in most environments because it is like a very heavy computational filter. But an environment like this one where these objects are not optimized at all and there's way too much stuff happening, honestly. It's all very high quality, high textured objects. So we're getting around 70-ish FPS, right? But then if you go over here and then there's no post-process, I'm going to add a post-process. The way you add post-process also is you just go to this volume. Where is it? Is it there? Yeah, post-process volume. Add it. Important thing to do is to unbound it so that it actually affects the entire scene. And inside of here, you can go to material plus and asset reference, and then I want the Kuwahara instance. It's applying now. So you can kind of see it works pretty well, even in like a more realistic environment, because these are all very high quality, high textured objects. Also, the FPS goes up a little bit just because of how unoptimized the actual environment was. That the shader helps it out a bit, which is a bit funny. But yeah, the Kuwahara filter, it's mainly used when you already have like a stylized scene on top of it, and then you put even more of a stylized effect on top of your already stylized models and everything. But you don't necessarily only have to use it like that. You can also use it in a more realistic setting, which I honestly really like. So yeah. But even if you go outside, then you can kind of see that it also works really well on trees. Sorry, that one's already has that effect to it, but yeah, you can use the effect on stuff that's not just really stylized, also a more realistic sense. Like if you want to stylize the game, but you don't have the ability to make all the assets yourself, and you have to download assets from the internet, right? But all the assets you find are like very realistic, high quality ones. This is a good way to kind of reduce that realisticness and then make it more, give it a more stylized feel to it. But yeah, that should be everything.